So it is my great pleasure to introduce Robert Miller, who's going to talk about classifying things quickly. And he was a PhD student at UW and is now a postdoc at MSRI in Berkeley. Thank you.
Thank you for the invitation to speak here with an open call. This is a job interview talk. I'm going to be giving this at least one interview in the next month or so. So please offer me any feedback or thoughts you have on it, if there are ways you think I could improve it, or better title or anything like that. This is the third time I've given this talk too, so I have had some practice, so you guys aren't guinea pigs. So when I say classifying things quickly, I mean computer implementations to enumerate over isomorphism classes of things. And you'll see what I mean by things as I start to go through this. There's some interesting examples later on. But for now, let's suppose that we have a finite group acting on a finite set. Right? So you're familiar with the orbit stabilizer formula. It gives you the order of the group in terms of the stabilizer of a point and its orbit. But the way I want to think about this is as the automorphism group of the point, or the object, or the thing, and its isomorphism class. So when I say isomorphism, I mean an element of G. So an isomorphism is just an element of G that takes one point to another, or one object to another. So for some examples, if Sn acts on the set of points 1 through 8, yes, William?
Are your slides available anywhere?
They will be after the talk.
Because I just missed the first slide and I'm lost for the rest of the
Sure. You're not lost, though. You're not lost. There's a group acting on a set. That's all, really.
I missed the first slide, so I didn't know what G and X were.
Yeah,
Okay.
so it's just a group acting on a set, and the notion is an element of the group acts as either an automorphism or an isomorphism, depending on whether it sends an object back to itself or not. Okay. So, for example, we have the symmetric group acting on the points 1 through n. So that's just the normal idea. The automorphism group of a point is going to be Sn minus 1, so it just needs to fix that point. If we look at the power set of the numbers 1 through n, and we let G be a subgroup, then automorphism groups in this terminology are setwise stabilizers of these sets of points. If we take the power set of the power set, this is just a collection of subsets of points 1 through n. So you could call these incidence structures. So in other words, hypergraphs, block designs, error correcting code, simplicial complexes, projective geometries are all examples of such ideas where not all of the blocks are permissible, but just some of them. So the problems we're interested in solving are computing the automorphism group, figuring out whether two objects are isomorphic or not under some element of the group, computing a canonical label, so something which is in the same isomorphism class as the object you start with, and given two objects in the isomorphism class, they have the same canonical label, so this is sort of like a unique representative of an isomorphism class. And our main motivation is the enumeration problem, so we want to list isomorphism class representatives so that every class appears exactly once. So we want to traverse the set under the action. So assuming that we have the first three problems solved, I'm going to start by explaining how we enumerate objects. So with X and G as before, G is a finite group acting on X, and we'll let G be a subgroup of Sn to fix notation. What we want is an augmentation scheme for X. So there's a finite set of objects that we start with, called the seed objects. For each object, we want to specify a set of children of the object. And for each object, we want one unique parent, so where that object should have come from in some sense. So we'll call the pair xy an augmentation if y is in the children of x. So C of x was already used for the canonical label, so K here stands for kinder. So we need the following properties. The set we start with shouldn't contain any isomorphs. For every object that we wish to discover, taking the parent function of that object enough times should get us back into the seed set. Or at least it should be isomorphic to something in the seed set, I should say. And for each x in x and g in g, we have that the image of X is a child of the image of its parent. So, in other words, if I've got some object and the image of our point is one of its children, how do I say this more elegantly? So the parent function tells you where it should have come from, right? So if I don't discover P of X, I better at least discover one of its isomorphs. And in the child set of that, I better have the object itself. This will make more sense when you actually see how the algorithm works. But the point is that all the user needs to provide, aside from figuring out the automorphism, isomorphism, canonical label problems, is they need to give us the seed set S, the function that gives you children of an object, and tell me what the parent of an object is. So those are three relatively simple functions. And then based on that, we can run the following algorithm. So I'm defining a function generate of X, which I'm going to call recursively. So the first thing I'm going to do is compute the automorphism group of the object X, compute its children, and look at the orbits of the automorphism group acting on the children. So already if I have two objects that are children of the same object and one of these automorphisms takes one to the other, they're duplicates already. So I can already throw those away. So if I pick one representative from each orbit and I compute the canonical label of that, I'm going to store the permutation taking the object, taking the child, to its canonical label. That'll be gamma sub y. So at this point, I'm going to compute the automorphism group of y. I'm going to ask this question on the second to last line here about whether the two objects are isomorphic. And note that I'm restricting the isomorphism question to the automorphism group of the child. So this will make more sense on the next slide where I prove that this technique works. But the point is that that second to last line gives me a condition. And if it passes the condition, then I add y to the list. I say, here's y, it's a new object, and I call generate on y, and I recurse from there. If I failed the test, then I just throw it away and forget about it. So why does this work? Well, that funny condition, p of the canonical label of y to the gamma y inverse, I'm asking whether that's isomorphic to x under the automorphism group of y. So if you stare at it for a minute and think about what this is really saying, it's the same thing as asking whether there's an element of the group that takes y to its canonical label and takes x to the parent of the canonical label of y. So sort of I'm taking the pair x, y, and under the same permutation, I'm translating it to parent of canonical label and canonical label. So that's what the question is really asking. That's how I determine whether or not to throw something away. So to see that this works, let's suppose that y is isomorphic to y prime, and y is a child of x, and y prime is a child of x prime. Now, if both y prime and y are added to the list, in other words, if I accept both of them, the assumption is that they're isomorphic. So this g that takes it to the canonical label of y, the canonical label of y prime will be the same object. So this g and g prime will take them to the same object. If I look at the parent of that object and take the inverses of the original ones, I'll get to x and x prime. So in other words, on the left side, I've got the pair xy is isomorphic to the pair p of c, c, and the same thing for x prime, y prime. So the isomorphism along the bottom guarantees that I have an isomorphism along the top. So if y and y prime are isomorphic, that means that x and x prime were isomorphic to start with, which means you can sort of trace isomorphisms all the way back up to the seed set. So that's why we need the seed set to be isomorph free. But you can easily take a set that's too big, just compute canonical labels and throw away duplicates or something. So that's not such a strict requirement. But the point is that any object that we can reach by looking at children of objects we'll get to in this way exactly once. So before I explain how the algorithm works in more detail, in other words, how we get the automorphism, isomorphism, canonical label functions, I'd like to go through some pretty interesting applications which illustrate sort of how general this method can be. So the first example is K-trees. So You can also generate normal trees, and you can generate graphs and things like this with this method as well. The way you would generate graphs is to look at the set of edges you could add to a graph and see where the automorphism group of the graph sends those edges, pick one from each orbit, and add that, and so forth. But these are more interesting examples, I think. So you can build k-trees by adding, you start with a k-click, which is a complete graph on k vertices. You add a vertex with k edges connected to a k-click. And you do this recursively. You just add another vertex, find a k-click in your tree, and add vertices to that click. So here's an example of a 1 tree, a 2 tree, a 3 tree, a 4 tree. And the idea for handling these things is that you can put an elimination ordering on the vertices so that you can sort of go backwards and delete a vertex that's connected to a click, and so forth. So
can you define what a k-tree actually is? You've explained one way of constructing them.
That's one way of defining it, is any graph that can be obtained by that
Is there a more
process.
intrinsic definition? I mean, like, you can define a tree intrinsically by saying no cycles.
Yeah, I'm not sure the exact definition, but I think a tree is something without any cycles. I think a k-tree is something without cycles of greater than a certain length. For example, a 2 tree will have triangles, but I don't think it'll have bigger cycles.
Does a 2 tree have like dangling edges, or does it just have triangles?
Every vertex gets added with two edges coming off of it.
Okay,
So there aren't going to be any degree 1 vertices. But so these come up in modeling social networks and things like that. Maybe the network in question is a subgraph of one of these things, so it's interesting to study these that way. Another example is error correcting codes. So here the idea is you have, this is the extended binary Golay code, so it's dimension 12, degree 24 binary code. The idea is that you think about this matrix, you want to view the code as the row space of the matrix. So if you have a message of length of 12 bits, you can encode it by using those bits as coefficients of the rows, and then you get a message of length 24. And the property of this code is that every vector in the row space has Hamming weight at least 8. So if you delete 3 bits at random or add 3 bits at random, there's still a unique word in the code that what you get is closest to. So codes are used for eliminating errors in transmitting information. And all of the optimal codes of length 32 are known, but I don't think this is known for 64. And it would be good to have all of the 64-bit codes figured out, and maybe even 128-bit. And the idea here is that you add words to the end of the generator matrix. So you sort of look at the different. So the automorphism group of the code I should mention is what you permute columns. So if you permute the columns and you get the same row space, you don't need to have the same matrix, but if you have the same row space, then that's an automorphism of the code. So knowing the symmetry groups of these codes and things helps when you're generating these. So a doubly even code, for example, is something where the Hamming weight is always divisible by 4. And those come up not only in coding theory, but also as topology types of these things called adinkras. So adinkras are, so they're graph isomorphic to a quotient of a cube by doubly even code. You have a bipartition of the vertices into bosons and fermions. Each color on an edge represents a different supersymmetric transformation. So if you're not familiar with physics, the idea is that bosons and fermions represent energy and mass carrying particles, and supersymmetric theories are supposed to try and explain the duality between, let's say, waves and particles. So the dashed edges mean that this particle actually gets sent to minus that particle. So this is in quantum physics, you have a superposition. So these are really the basis of a vector space. And the idea is each supermultiplet represents a different supersymmetric theory. And if you're trying to classify these, quite a lot of the supermultiplets have this adinkreic structure. And you can classify the doubly even codes that encode their topology, and then you can classify the different ways that you can raise their levels so that the heights of the vertices are also part of the data. And when you start, you have all of the white vertices on the bottom and all the black vertices on the next level up, and then you can look at the different ways of raising the levels. So there's the double even code classification, the way of raising the levels. And you think about raising these levels as augmentations as well. So the children of an adinkra would be, pick a vertex that can be sort of flipped up to the next level, and look at the automorphism group and see which ones are equivalent, et cetera. Run the algorithm that way. So the automorphisms of this thing are going to fix colors, they're going to fix levels, and they're going to be graph isomorphisms as well. Another application would be the classification of reflexive polytopes. So these are, essentially you've got the convex hull of a finite number of points, and you're required, so reflexive means that the interior contains exactly one point. And the way you augment these is you just add another point such that you don't add any more interior points, and you take the convex hull of that together with the previous polytope. So this has been up to, I think, 4 dimensions, and it would be nice to carry things further than that. There's quite a bit of blow up with these. I mean, you've got, I think it's 16 in 2 dimensions and 4 digits in 3 dimensions, and maybe 9 or 10 or more digits in the next dimension up. So it stops quickly, but it would be nice to sort of see at least what one more dimension would do to the counter.
Is any hope? I mean, this of course like points that are already thought about that a long time ago, and there's maybe there's some guesses from how it grows, but it's almost certainly out of the reach of enumeration.
Yeah, I mean, we might be able to get one more dimension, maybe, but
even that
it's,
seems to be helpful.
it's not like.
Any reasonable hope to get that?
Well, the good thing about this method is that it doesn't just give an exhaustive enumeration of everything. So if I run the algorithm as I did before, and I decide to accept an object under the algorithm I described, I can also, with a fixed probability, throw it away anyway. And so at the end of the day, if I pick pretty high probabilities of throwing things away, I'll throw most of the things away, and I'll have a chance of actually terminating the algorithm. And what you get then is the number of objects generated is an unbiased estimator for the total number of objects in the isomorphism class divided by the probabilities that you took. So it's not just useful in enumerating everything, it's also useful in taking samples of things. So another example of objects that we can look at are, given a particular graph, we can ask what are the different embeddings of this graph onto a surface. And the picture I've drawn here is only good for surfaces of positive genus, so compact orientable surfaces. But non-orientable surfaces also admit a pretty similar algorithm as this one. So in this one, so you should think of the green and the blue as all one color. The idea is that the black edges represent actual edges of the graph, and the colored edges sort of tell me how the vertices are arranged around one another, sorry, how the edges are arranged around a vertex locally at that part of the embedding into the surface. So this is resembling, on the left is a partial embedding of the complete graph K4, and on the right is the complete embedding. So the idea is that these 3 green points represent one vertex, and the fact that they're sort of off on their own, not connected, means I haven't yet decided which way to bring the edges together on the surface. But once you get all of the rotations around all of the vertices fixed, you've got an embedding, and augmentations consist of the different ways of gluing the vertices together, or gluing the ends of the edges together. So another application is generating quadratic forms, or equivalently generating lattices up to isometry. So here, it might not be so obvious that the isometries are sort of living in some permutation group, but an isometry has to preserve length, and each lattice has a finite number of vectors of a given length. So if you start with a basis with lengths L1, L2 through Ln, and you look at all of the vectors of those lengths, you know that each basis vector has to stay within that orbit. So there's some number where it actually is it actually is living inside of some permutation group, so the same techniques work. So the idea is here you augment by adding a basis element to the lattice and saying what's its length and what is its angle to all the other vectors that we already have. So here's a picture of the group lattice E3. Another application is we can generate subgroups of the modular group of a fixed index. So here the idea is that we have these two generators of the modular group. One is order 2 and the other is order 3. And if n is the index of the subgroup you're considering, you can represent that subgroup up to conjugacy by a graph with 2 cycles of one color and 3 cycles of another color. And those 2 and 3 cycles represent what these generators do to each of the cosets. So again, augmentation is either add a 3 cycle of one color or add a 2 cycle of another color, and by the time every vertex touches one of these cycles in exactly one place, you've got a full description of the action on the cosets. And then all you have to do is pick a vertex, and that acts as the identity, and then using the Todd-Coxer algorithm, you can actually compute generators for the subgroup. And again, the permutation action on the graph translates to sort of isomorphism type of these subgroups. This one's pretty interesting. So space fullerenes. So you're probably familiar with fullerenes. Its faces are regular polygons of size 3, 5, or 6, and a space fullerene is a tiling of 3 space by fullerenes. So there are non-periodic tilings. There are quite a lot of tilings in general. But if you have a periodic tiling with a finite fundamental domain, and you can actually sort of get all of the data written down in a finite amount of space, then you can start with these tilings, take each fullerene and shrink it within where it lives, attach a fullerene to each vertex of the one that you've shrunk, and then add what's called a prism to each face. So the prism is you have 2 polygons of the same size on either side, and you have 2 rings of interleaved pentagons going around the middle. So this is another way to use this software to generate things which are cool and have nifty pictures. So how it works is via partition refinement, so that's what I've been working on this week. So if G is a subgroup of Sn, then we want to look at these ordered partitions. So it's not only a partition of the set 1 through n into cells, but it's a specification of an ordering of the cells. So in other words, the cells can't move amongst themselves, but the elements inside the cells can. So typically we'll start with a unit partition and start refining it down until we get to the discrete partition. Unit partition has 1 cell, and the discrete partition, every cell is a singleton. So since these partitions are ordered, discrete partitions give you orderings of the vertices, and unit partitions give you essentially no information. So we also consider partition stacks. So looking at this picture sort of shows you the notion of finer than. So not only does each cell of one partition need to be contained in a cell of the other one, but they need to show up in the right order. So this gives you an example. Each partition is finer than the partition before it. And in this picture, it's strictly finer than. And at the top, we have a unit partition. At the bottom, we have a discrete partition. So sort of at each step, we want to get more information about the potential ordering of the points that we're considering. So this sort of gives you an idea of how these get stored on the computer, since these are actually the same exact situation, because the ordering doesn't matter within a cell. So in other words, we just need to write down the order of the elements and where each cell break appears for the first time. So that this shows you can actually store these things in linear space. So the next concept we need is an equitable refinement. Essentially, an equitable refinement for an object is just something where any automorphism that doesn't move things outside of a cell can move everything within a cell to anything else in the cell. So it's sort of like being transitive on each cell. So I want to define the action of G on these partitions by just sort of permuting the sets in the natural way. Aught G of x pi is going to respect the partition as well. So this means that elements can move within the cell, but not outside. As I said, so equitable, one way of defining it is saying that the cells of pi are equal to the orbits of the automorphisms that respect the partition. In other words, if you look at all the automorphisms, everything moves by some element of this restricted automorphism group. So now I want to define R of x pi, at least for now, as the coarsest equitable refinement. So it's basically you take this aught g of x pi, look at its orbits, and in practice you define a certain ordering on these things, but it's a bit technical for a 1 hour talk. So I'll come back to that a little later on, but I'll just sort of give a hint. So one property of the coarsest equitable refinement is that if you take the set of automorphisms that respect a partition, they're also going to respect the coarsest equitable refinement, and in fact the two groups are equal. If you act on an object and a partition by a group element G, that's like conjugating the automorphism group itself. So the sort of natural way to act on groups with these objects is by conjugation, whereas you act on points, objects, and partitions by just permuting the objects themselves. So that's sort of pretty natural group theory. So if C1 through CK are the orbits of a subgroup, then the orbits of the conjugate of the subgroup are the images of these cells. That tells us that the coarsest equitable refinement also has this natural property with respect to action of G. And pi is equitable if and only if pi to the G is equitable for x to the G. So the equitable property also respects the group action. Okay, so the way we compute all these objects, so we want to know what the automorphism group of an object is, how to tell whether two objects are isomorphic, we want to compute canonical labels. So we do this by searching through a tree of nested partitions, or partition stacks. So what we do is we take the coarsest equitable refinement of the unit partition to start, and then we look at we put a tree structure on these stacks. So the parent of a node is you delete the bottom stack, right? You can, if you're thinking about the tree in your head, you can just have a partition at each level of the tree, and the partition directly above is just, coarser than the one below it. And the leaves of the tree are discrete partitions. So we start with this sort of coarsest equitable refinement. So we start with a unit partition, and then we, let's say you start with a graph, right? So the coarsest equitable refinement, for example, each cell, every vertex will have the same degree. So you sort of, you have, an automorphism has to take this point to that point, so that's where you start. And then you sort of break up the partition more and more until you get a discrete ordering, and you look at the different leaves of the tree to see what orderings you get. So if we have an automorphism of the object, applying it to the entries of the partition stack gives us an automorphism of the search tree. So when we're searching through this tree and we discover an automorphism, that means that there are large pieces of the tree we never have to look at again. The root maps to itself under this action. The image of each equitable partition is equitable. That's basically what those slides showing that the action of G is sort of natural amongst all these objects shows, is that you get an action on the search tree. So I'm going to tell you now about how to compute the automorphism group. So given a partition stack ending in this partition, so if we're looking at the partition pi, which is C1 through CK, we pick the first cell of smallest size. We pick a point inside that cell, and we split it out. We sort of fix it at the beginning, and we say, okay, now what happens? Right? So we'll go through each point in that cell and put it at the beginning and see the different partitions we get. Those are sort of the children of this partition in the search tree. So technically the children are, we call this refinement function on it, because for example, if you've got the K cycle and you fix one vertex, you're almost fixing everything. The only thing you can do is sort of flip. So that'll say that the neighbors of those are in a cell and the neighbors of those are in a cell. So this R function really shrinks the part of the tree that we look at. So this gives us a subtree of T of GX where we actually search. So if we start at row, which remember was the refinement of the unit partition, we go through the process I just described, and every time we come to a discrete partition, we look at what the ordering tells us. So the first time we just sort of write down that order. And then any other time we come to a leaf, we look at the permutation that takes AI to BI. So A1 through AN is the first one we come to, and B1 through BN is the, let's say the next one we come to. So we look at the permutation taking AI to BI. If it's an automorphism, that means that the two parts of the tree, so we've got these two leaves of the tree. So if we follow them up towards the root of the tree, eventually they'll join up. And if we look at the subtrees from where they join up, so we've got sort of two trees rooted at one down from where they join, those two trees are isomorphic under this symmetry. So that means that if we're looking at one, we don't have to search the rest of this second tree. We just go all the way back up to where they met. Once we finish searching the whole tree, if we backtrack off the tree, then all of the automorphisms we've discovered give us a set of generators for the automorphism group. So, and a little bit more technical details, the points that we split off of the partitions that get us down to the first discrete partition are known as a base in computational group theory. So, in other words, if we fix those points, we fix the whole group. And by using some permutation group algorithms, we can take advantage of the fact that we have a base now, and we can compute a very good data structure for the output group that we're trying to compute as we keep searching through. So if I pick a different point and place it first, that means that our base point is mapping to that point, and that sort of gives us a way of traversing through the group. Okay, so that's how you compute the automorphism group in very brief terms. So when we compute the canonical label, we also ask that whatever function is actually computing R of x pi also computes what I like to think of as an invariant. So if I have an element of the group and I permute the object in the partition by that element, the refinement process should give the same invariant. So that way, if I have two objects which are isomorphic under G, and I give them the same input, the same refinement will happen and the same invariant will pop out. So to compute the canonical label, I try to maximize these invariants as I'm searching through the tree. The problem is your invariant might not be, in computer science terms it might be a hash, but it might have collisions, right? You might have two different objects with the same set of invariants going down. So at that point, we need to resort to a lexicographic ordering on the objects. So at that point, you have to say, actually, here's two candidates, and you just have to sort of define some arbitrary ordering where you pick the largest one. But the point is that if I permute my object by some element of the group, the invariants will all be the same, and I'll pick the same object at the end. So normally, if we have a discrete partition L1 through Ln, that gives us a relabeling where Li goes to I. If G is a strict subgroup of Sn, the relabeling is more complicated because the one I've written down isn't necessarily in the group. But again, using these permutation group algorithms and base change, you can define an element that's actually in G. And that was one of the things I figured out on the plane ride down here, which let me sort of finish the implementation. So that gives us the canonical label. And it's going to be the same if we permute the input by any element of our input group. And because the relabeling is also in our group, if we permute by an element not in the group, they're guaranteed not to be the same. So computing isomorphisms is very similar, but now we start with two objects. So we take the first object and we refine down until we get a discrete partition, and then we just start doing the search tree for the second object. And when we're looking at the search tree for the second object, we're looking for refinements that went the same, all the indicators should be the same, and the structure of the permutation stacks should all be the same. And at the very end, if we get two discrete partitions, so A1 through AN is the only one we'll ever see for the left object, but for the right one, we're going to consider all these different ones. And we'll just test whether AI goes to BI as an isomorphism or not. If it is an isomorphism, we're done, right? We just return from the whole function. And if it's not, well, we're searching through the tree for the right one. We'll record automorphisms as we discover them to prune the tree, just like when we're doing the automorphism group. But if we discover an isomorphism early, we really don't need to do much. And if they're isomorphic, chances are good that we'll find it pretty quickly. So that's how you answer the 3 questions of automorphism, group, canonical label, and isomorphism. And given those tools, it's pretty easy to define an augmentation scheme. You just need to implement those other 3 functions, which give you the objects to start with, the children, and 1 parent. So in practice, the refinement function isn't actually that hard to implement if you can define, okay, so here are the properties that it needs to satisfy. It needs to be invariant under the action of the group, and it needs to it needs to respect this analog of the coarsest equitable refinement property. If I replace the partition with the output of the refinement function, I shouldn't lose any automorphisms. And also, it's a refinement, so the output had better be finer than the input, at least as fine as. So we could just return nothing, but that's not going to be very efficient. But to get an idea of how easy this is to implement, essentially you just need to implement a function that takes an object, a point, and a set, and gives you a number. And the number just needs to be invariant under permutations acting on the object, the point, and the set. For example, if I have a graph, if I have a set of vertices and another vertex, the number would be the number of edges from that vertex to the set. So you're sort of refining by degree. So if you implement a function f that gives you these invariant numbers, you tell me how to act on an object by a permutation, and you give me some arbitrary lexicographic ordering on objects, then Sage will do the rest. So the point is those 6 functions are all you need to implement to have all of these problems solved for your class of objects. And they're pretty trivial functions to implement. So it's all in Sage groups, perm groups, part and ref. Until last night, actually, only the full symmetric group was supported. But now you can do arbitrary subgroups, and this is on track 10804. And I've actually, I've even run Valgrind tests on everything, and things seem to be working. I'm getting correct answers for some rather basic questions, so the rest of my time this week is going to be developing more and more complicated tests of this thing to try and chase out the bugs that are still there. But that's the fun part, because now I get to implement these specific objects and see what they do all these a side effect of this is that now there's sort of basic data structures for dealing with permutation groups in Sage. Before, the only way we had of dealing with permutation groups was through gap. But because these algorithms are written in Python, they're very low-level C functions, I couldn't keep farming out all these calculations to gap because the overhead would have been too much, and I wasn't about to wait for the gap to finish being implemented. So,
No, it's
well, it's a worthy goal, and the more
How does
we
this
get, the
compare
better.
to what's in gap?
So right now, it's sort of a basic implementation of the function. So there's
I mean, but
maybe-
does gap have code for partition refinement? I mean, or for similar
not that I
stuff?
know of. I mean,
How does gap do what it does if it doesn't have the same code you have?
well, if you want graph isomorphism, you have to download this optional grape package, which
Yeah.
packages naughty.
Right.
I think there are some basic partition refinement stuff that Steve Linden did, but I don't think that it goes nearly as far as that. I think that the way it does things like, so if, let's say the set of objects you're acting on are permutations in Sn itself, and G in your given group acts by, so G acts on gamma by sending gamma to G inverse gamma. So the automorphism group is trivial because the only G that's going to send G inverse gamma to gamma is the identity, but the isomorphism classes are right cosets of your group G. So for example, one of the test functions I have right now computes a coset traversal of a subgroup of Sn. So you can also sort of phrase things the right way and come up with the right object set where the automorphism group aught sub G of X, you can think of X as another group, so this will compute the intersection of 2 permutation groups. And there, I think it uses a modified copy of Leon,
I see.
which sort of implements all this stuff, but maybe not in as full of generality as this. Also leaks memory everywhere, and the canonical label thing isn't actually implemented in Leon. Like he mentions it in his first paper. It will appear in paper 2, which never appeared. That's why I had to come up with this idea on the plane, because it's not in the literature. So I think this sort of completes that chain of ideas, and then because we have canonical label restricted to a subgroup, we get all this canonical augmentation stuff in the most general way possible. I haven't done benchmarking with GAP yet, because my primary goal wasn't to get a competitive replacement for permutation groups. I just wanted to implement some sort of permutation group structure along the way, and then optimize it later once I get the canonical augmentation stuff started. But I mean, right now it's pretty bad. Like if you want to, if you've got S15 represented as one of these objects, and you want to change the base, it'll hang indefinitely, because the algorithm it does is I think it's at least n to the 5, and the worst cases are sort of Sn and An. I mean, there's tricks there, because if it's Sn, you know what the stabilizer of a point in Sn is without thinking, but it's doing it the hard way, because it doesn't know about the structure automatically. But after I get all these tests in, I'll write these implementations, and things should get better pretty quickly.
You said that when you're testing isomorphism, that if objects were isomorphic, you'd find that pretty quickly, but if they're not isomorphic, you'd have to traverse the whole tree and take a long time.
Well, it takes as long as it does to compute the automorphism group of the right-hand object.
I was expecting it to be the other way around, that if things were not isomorphic, you should be able to find it out pretty quickly. There'd be some property that they...
Actually, yes. So in general, given 2 random graphs, for example, you'll find out they're not isomorphic almost instantaneously.
You just look
Because
at the degree sequence.
the degree sequence is part of the information when you call that refinement function in the unit partition. So I misspoke a bit there, but the point I was really trying to make is if they are isomorphic, it's not like you have to search through 3/4 of the tree to find it. Because it'll sort of, by a similar idea, if you take a random graph and call a refinement function on it, it'll be almost discrete right there. So there are very few things left to do. The tricky ones are highly symmetric things. Yeah.
Robert, these graphs, I can't find the name, like Meter-Gaza graphs or something like that. They're really hard for partition.
Yeah, I mean, according to the naughty mailing list, what's the incidence structures of some kind of design or something? There's some test case which is really hard for this stuff.
I was reading about these graphs.
Very cool.
If you're highly symmetric, then you discover automorphisms all the time, and you're constantly pruning the tree. It goes quickly. If you're not symmetric at all, then the refinement function is going to blast everything away. So you have to have just the perfect storm of symmetry to really stump this algorithm. Right now I'm just trying to get a generalized implementation that doesn't bug out, and then do optimizations from there. So this is still sort of in the first phase of development. But the eventual goal is to be able to be competitive with Mackay's software. Not as fast as, because his software is only for graphs and only for simple graphs, and this software deals with very, very general kinds of objects, so it's sort of a different goal, but it would still be nice to be on the same page as he is.
Right, any more questions?
So when you're done, Sage will have the capability to, I can ask it, go through all codes of certain length and dimension. It will very efficiently go through that, and yeah, I can provide a test for that. Like, let's say I want to go through all those codes and test for some property.
Yeah, and the way the algorithm works is you can have it just give you the code and then not do anything until you're done with it. You can actually implement iterators so that it doesn't save that code if you don't want it. You can just deallocate it yourself and then keep going.
By the way, currently for codes of even length 32, there are still gaps in the tables. Online there are tables for the best known codes. So even 32 bits,
Binary codes?
Binary codes.
Binary linear codes?
That there's still, I mean, there are tiny gaps of one between upper and lower bound. But
Cool. So there's problems we could probably solve with this.
if it's
As far as I
efficient,
know,
if
the
it's
stuff for
efficient,
generating codes is state of the art. I haven't met anyone else who's using this sort of augmentation scheme in this generality.
Yeah, I heard a talk on that at a meeting a couple of years ago by Gabriella Neighbor, and I was pretty surprised. She said that the algorithm for testing isomorphisms between codes is this algorithm of Leon. It's like Enumeration.
Yeah.
That has been around for a long time and no one's come up with anything
1991.
better yet.
Yeah.
So
Yeah, I think it.
there's a market for this.
Yeah.
If your algorithm is more efficient than his.
I mean, I have made some decisions in the interest of sort of, when Leon does things, he keeps track of every break he does at every step of every size and exactly what happens to everything. Whereas Mackay's idea and what my software does is it sort of just spits out numbers and multiplies them together and sort of creates a hash of the situation. Instead of actually storing everything that happens at every step, it sort of gives you a number that probably won't be the same unless they were the same. So that might be one way in which it's more efficient. Another way is that when I keep track of which point I split out at each point, and then I have another sequence, what he does is he changes base at every refinement. So he looks at all of the fixed points of the partition, changes the base on the group for that, and then says, well, what are the orbits under that, and then refines the partition by that. What I do is I change the base once when I get down to the first partition, and then any other time I've got these other fixed points. The base is conjugate to the other base by, this element goes to this element, that element goes to that element. So I don't need to change base every time I do it. I just sort of map the permutation back over by that element, do the intersection with orbits there, and then sort of map it back. So I don't think I'm losing too much in the ability to split up cells, but I'm not doing all these base changes all over the place. At least that's what he describes in his paper. I haven't gone back and looked at his code in a while. So.
The one time I met Leon was at a Magma conference in Milwaukee. Does that mean is his algorithm implemented in Magma?
His code is what's in Magma 2. In fact, now I'm not surprised because his code, so he indexes starting at 1 instead of 0 because he's a mathematician. And there's nothing wrong with that except when he allocates memory, he allocates, like every allocation is +1 at the end. Because he starts at 0, so he just sort of, I guess he just sort of started allocating +1. Except for every once in a while there's a +2, and you're not sure, maybe something just seg-faulted, and he just sort of added 1. I don't know, I haven't looked at this close enough, but Tom Boothby and I looked at his software and tried to actually deallocate everything correctly so that we could use it as a library, because we wanted to use it in Sage like, the right way. And it seemed like very powerful software and very useful to be in Sage.
But it was a Magma program.
So I have, I think Alan Steele has done that for Magma. I think that's why it works in Magma. But Tom Boothby described it not as leaking memory, but as splattering it. So it was kind of, we spent a good part of a month, freeing memory and fixing things and looking through Valgrind logs. And it was just, it was a bit messy. But given that, when I was first started working with these codes in Magma, there was a bug, and essentially, it was weird. It would if I remember correctly, it wouldn't hang, or it wouldn't crash completely. It would just hang. So some of these codes take a while to do these computations anyway, and every once in a while it would sort of take a while and then move along, and other times it would just stop, like utterly stop. So. At the time I didn't know about Leon's code, and I didn't know what to do, so I just started implementing these things in Sage because it was pretty similar to the graph isomorphism algorithm that had already been done. And, that was my only way to get around the Magma bug, was to